let's welcome Dr. Lisa Mingzhe Sun. She is an instrumentation scientist at Surface Measurement Systems and holds a PhD from City University of Hong Kong. Her research primarily involves developing porous materials such as zeolites, MOFs, layer double hydroxides, and biochar for carbon capture in VOC and O2 removal. Currently, she's broadening her scope to encompass diverse CCUS applications, including membrane separation, mineral carbonation, calcium looping, and amine-based carbon capture. Lisa, without further ado, the floor is yours.
Okay, thank you very much for the introduction. Let me show my slides. Okay, let's get started. So, hello everybody, I'm Lisa Sun, and today I would like to introduce our new product, BTA Frontier, a self-contained competitive breakthrough analyzer to all of you. And during today's talk, I will first introduce our instrument, from the fundamental to the mechanism to the hardware and software. And after that, I will use two case studies to show you how to evaluate your material using our instrument. And the two case studies include the CO2 capture and the VOC capture. Okay, so let's get started from the BTA fundamentals. The breakthrough analysis is a suction technique for measuring breakthrough curves, tracking how your materials and the gas molecules interaction over the time. And by doing the experiments, you can have a lot of insights. For example, the gas uptakes, we also call it capacity, as well as the selectivity among different types of gases. And you can also get some breakthrough or equilibrium time, or the heat transfer, the mass transfer, the kinetics if you do further analysis. And if you have a look at the figure on the left hand, it shows the basic mechanism. It is quite simple. So first, you prepare the target gas mixture, and after that, you feed the gas into the system and into the column, and where you put your sample inside. And at the outlet, you use a couple of sensors for the measurement of the gas concentrations. And below here is the typical breakthrough curve showing the whole process of absorption. So at the beginning, when you push the gas into the column, you will determine nothing at the outlet. So that's why the C by C naught is 0 at this time. And after some time, when the material is getting saturate gradually, the molecules will start to coming out. And here we call it the breakthrough point. And after some time, the concentration is increasing and finally reaches to the equilibrium, to the feed gas concentration. So here, during this process, we call it the breakthrough. And from the gas appears from the beginning, the breakthrough here, and to the end of the equilibrium, we call this zone as the mass transfer zone. And the slope of the curve here represents the kinetics of this breakthrough process. So typically, especially in the industrial process, people would like this mass transfer zone as shorter as possible. So that means the slope is steeper as possible. Okay, so next I will show you some potential applications, how our instrument can help on your studies or researches. If you are focusing or interested in the carbon capture, utilization, and storage, you can use our instrument to evaluate your samples. And you can also do the material characterization, the VOC capture and removal, as well as to study the absorbance process at scale up. And we also have the different sizes of the column, enable you to use various types of your materials, including like the spheres with different sizes or the monoliths. Okay, so here I will show you the specifications of our instrument. We have 6 different gas or vapor inlets or sources. So 6 MFCs, and you can connect the gas, for example, the CO2, nitrogen, air, etc. And we also have the 2 reservoirs. You can put the solutions, either the water or the organic solutions inside, and using the bubbling method, you can generate the vapors, like the water vapor or organic vapors. And we can generate the water vapor from 0 to 95% RH. And for the amount of sample used, it is one of the interests of the customer, because especially for the researchers, they want to use small amount of sample for the test, especially at the beginning, or if you want to screen the samples at the beginning. And for some sample, like mouth sample, it is very difficult to synthesize. So they do not have a lot of samples. And we do have the small columns with the internal diameter of 2, 3, 4 millimeter. And on the other hand, we also have the large size column. It is 10 millimeter internal diameter. So this flexibility enables you to optimize like the size of your samples to achieve like both the high gas removal or absorption efficiency, as well as the faster kinetics. Okay, so in this system, we have a series of sensors for gas measurement. We have the CO2 sensors for ppm level or percent level. So if you are interested in direct air capture, BAC, you can use the ppm level CO2 sensor. And if you are interested in PCC post-combustion applications, you can use the percent level CO2 sensor. And we have the water vapor sensor. And we also have the sensor, PID sensor, for VOCs measurement at different ranges from ppb level to percent level. And finally, we also have the thermal conductivity detector, and that is used for the helium, the measurement of the helium. Like if you want to measure the that volume using helium gas, you can use the TCD. Okay, so for the temperature control, we have two systems. The first one is the incubator. So if you look at the photo here of our instrument, here we call it the incubator. And the temperature of the incubator can be controlled from 5 to 60 degrees C. So in the incubator, we have the reservoirs here where you generate the vapors. And we have the samples here. We have the sensors here. So stable temperature control is very important to have an accurate measurement of your sample. And another part is this column other here. It is the local heating of your sample. So if you want to do the in situ sample activation or regeneration at high temperature, the highest temperature can reach up to 500 degrees C. Or you can do some absorption or reaction using this local heating here. Okay, and we also have the thermocouple inserted in the column. So by doing this, you can easily measure the temperature during the absorption or reaction process, and you can have an idea if there is endothermic or exothermic of the absorption process. Okay, so for this system, we have the two-column system. So that means you can put two columns simultaneously in a system, and it is very time saving. If you want to, for example, during the weekend, run the method, just put the two samples and run the method in sequence. That is time saving. You do not need to come to the lab to swap your samples. And the next thing is the gas preparation system. So here, this one I would like to highlight because this one enables you to generate the very uniform gas mixture. For example, if you want to mix CO2, water, or other organic compounds, VOCs, for the generation, it needs a little bit of time. And for the thorough mixing, it also needs a little bit of time. So during this process, you can do the mixing through the vent. The gas preparation will only go to the vent rather than go to the system. And at the same time, you can purge your system, either the sensors or the sample, use the purge gas. So you can do this during the cooling or activation. It is time saving. You can do that simultaneously. And so this part enables a very accurate gas preparation. And at the outlet, we also have the capability to connect the exhaust to other type of gas detectors. For example, the mass spectrometer, the gas chromatography or FTR, etc., for further analysis, if you like. And the size of the equipment, it is not that large. You can just put on the laboratory bench. Okay, so here are the key features of this instrument. And the first one is it is advanced and cost-effective. As I mentioned, we have a series of different type of sensors like CO2, water, VOC sensors equipped in our system. So if your application is about like either the carbon capture or VOC capture, this instrument is smart enough. You do not need an additional mass spectrometer. And the second thing is optimized for small samples. As I mentioned, we have very small columns, and you can use small amount of sample. It is very researcher friendly. And for the precision, it is very good because, for example, for the gas generation or the preparation for the measurement, all these environment, the temperature can be well controlled, and the gas generation is also very good. So this one is the premise for an accurate measurement. And this system is ideally for CO2 and VOC capture, but on the other hand, you can also extend applications to other type of gases like the olefin or paraffin or other gases, just to connect the exhauster to other gas analyzers. And it is very user-friendly. So from the operation, the software, the analysis software, the control software, it is very easy. And I will briefly show you later. Okay, so here comes to the schematic of this instrument. Let's get started from the gas or vapor generations. So here we have 5 mass flow controllers, and you can connect the mass flow controllers to the gas cylinders, and you can also have the solutions in the reservoirs. We have 2 heated reservoirs here for the solution, the vapor generations. And after that, we have the first sensor for relative humidity measurement. And after that, we have the gas preparation and analysis system for the uniform gas generation. And after that, we have the pressure indicator. You can find that we have 2 pressure indicators in the system, both inlet and outlet. So by having this, you can easily tell if your material is suitable for the test. For example, if it is a very fine powder, we do not recommend for the breakthrough analysis because there will be a lot of pressure drop, and you can easily have this information from the pressure indicators. And we have the injection ports here. And so here, the purpose of having this is to calibrate the PID sensors, because the PID sensors is not specific sensors for the type of the VOCs. You need to do the calibrations when you change the type of the VOCs. And typically, there are 2 approaches for the calibrations. The first one, you can use the standard gas cylinders. It is very good, but on the other hand, maybe very expensive, especially you want to measure a couple of different type of VOCs. And another approach is you just use the saturate pressure vapor and to do the calibration using these injection ports. You inject a different amount of organic vapors, and you can do the calibration for the PID sensors. Okay, so after that, we have 2 lines here, and the top line here is the bypass line, and this one is through the column. So if you want to push your gas like directly to the sensors, you choose the bypass line, and if you want to start this experiment, you just switch the valve to the column. And in the column, we have the 2 column system, and we also have you can also put the column with different sizes. Okay, and after that, here comes to a series of different sensors. First is the sensor for relative humidity at the outlet, and the CO2 sensor, we have either the ppm level or percent level sensor. And the PID sensor, different ranges from PID to percent level. And the TCD sensor, thermal conductivity detector. So for the detector, TCD here, well, as I mentioned, you can measure the depth volume, if you use the helium as the gas. And on the other hand, if you also want to do some measurement, for example, in the gas mixture, you have CO2, water, and methane, and you want to measure the methane. So you will have, from the TCD, you have an overall reading of the 3 gas components. And from these sensors, you have the individual reading of CO2 and water. And by deconvolution, you can also get the reading of methane. But in this case, you need to do some calibrations. And finally, we have the mass flow meters here. And there are 2 purposes of having this mass flow meter. The first one, very simple, to check the leak in the system. Every time before the experiment, I will recommend to check the leak, especially after you assemble your columns here. You need to make sure there's no leak in the system. And another purpose of this MF mass flow meter is to monitor the real-time mass flow rates. So, for example, during the absorption or desorption process, a lot of process, the flow rates is not the same what you purge into the system. It will change. For example, during the molecules interact with your materials or keep dissolving from the material, the mass flow rate changes. And if the customer, they want to have a very accurate calculation for the capacity, they need this mass flow meter. So we have the possibility here. Okay, so next I will show our sensors here. Well, I should say the secret of our self-contained nature of this breakthrough analyzer is we have the sensors integrated in the system. We have CO2 sensor at different concentrations, ppm level, or the percent level sensor. We also have the relative humidity sensor and the PID sensor from ppb to percent level. And finally, is the TCD sensor. Okay. So next, I will introduce the software, and the first part is the control software. It's about the data display, and you can find that during you run the experiment, you can easily monitor what is the concentration or the temperature or either the flow rates. If they're stable during the measurement, you can simply select what you are interested, these parameters here, and change the color here if you like. And it is very simple, and you can also change the time scale or the scale of the y-axis of the concentrations. And the next is about the method building. So here we enables you to build your own method, and it is very flexible. In each stage, you can define what is the duration of this step, and what is the temperature, like the incubator temperature, the column oven temperature, or the mass flow rates from all the MFCs. And you can choose if it is through the bypass or column, or which column, or if it is preparation or analysis. And I believe during my talking, you may feel a little bit confused because there are too many information. So finally, we have another column here that is for the user to input some notes to remind what is happening for this specific stage. So it will be very helpful, especially for the fresh users. And next, you can combine the individual methods in our sequence. So this is very helpful and very smart, I should say. Well, definitely you can design a method from activation or purge system, or to absorption, desorption, cyclic test, all these steps in one single method. But when you do the analysis, you will feel very painful because you need to select the proper duration for the data analysis. But if you have the sequence here, you can combine the individual method, and for the results you obtain, it is the individual reading from different methods. For example, if you only want to do the analysis for the absorption process, you just open the data of the absorption, and you will all the data there is about absorption rather than the purge or other desorption, etc. It is very convenient. Okay, so after that is about the data plotting. So first you input the data to our analysis software, and you can choose which parameter you are interested, like the flow rates, the temperature, or the gas concentrations. And after that, you can generate the figure like this. And this figure is automatically generated by our software. It is very simple. And the last thing is about the calculation. So after the measurement, if you want to do the calculation for water uptake or CO2 uptake or VOC or other type of gases from different sensors like TCD or mass spectrometer, we have the options here. And you can just simply input the amount of the sample and to define where to start for the calculation. And if you have the volume of that volume, you can input here, and that volume will be subtracted automatically by this software. So it is very smart for the calculation of the gas capacity. Okay, so next I will use the case study to show you how to evaluate the gas absorption under the realistic conditions. And the material we select is the Zeolite. It is a very, very popular material, widely used for a couple of different applications like the natural gas or air purification or VOC removal, gas separation, etc. But for CO2 capture, I should say it is not that widely used because it is highly hydrophilic. And let me show you why this feature will affect its usage in the real world applications. And for the carbon dioxide capture, there are two typical sources. First is the CO2 already released in the atmosphere, and we call that the DAC, direct capture. And another one is from the CO2 released in the industrial process. Before its emission, we want to capture the CO2 to prevent the release. And the challenges of these two both applications, the first one is the low CO2 concentration. So for the DAC, the CO2 concentration is only about 400 ppm. And for the post-combustion, it's around 3 to 50%. Well, actually, when we talk about CO2 capture, that means to selectively absorb CO2 from the gas mixture. So in this case, you need to consider not only CO2 itself, but also the other competitives in the gas mixtures. For example, the water, we cannot avoid its presence in the applications. And for these applications, I should say the relative humidity can be very high, like 60 or up to 100% relative humidity. So in this case, you need to verify or evaluate your material, what is the performance under the very humid conditions. And the first application is about the post-combustion carbon capture. So here, this figure describes this process is very simple. First, you have the flue here, and you burn it in the combustion chamber. After that, you will get the flue gas. And here, in this chamber, you put a solvent inside. And after that, people want to separate the CO2 from the flue gas. So you will have the pure CO2 here, and you can use it for further storage or utilization. And for the flue gas, you will have a, well, I should say clean flue gas without CO2. And the condition of this working environment, it is the for CO2 concentration is 3 to 50%, and the humidity can be very high. And next, I will show you the data, how we do the experiment. So first, we select the CO2 concentration of 50%. And first, we did the dry CO2 absorption at 25 degrees C. This curve is obtained from the breakthrough analyzer. After that, we compare the capacity with the isotherm we obtained from the DVS system. That is the gravimetric system in our company to measure the isotherms here. When you do the comparison, you can find that it is very consistent. That means the high accuracy of our instrument, the breakthrough analyzer, to do the measurement. Okay. And after that, we also conducted the water suction at different relative humidities from 10% to 70%. And this data is obtained from the BTA breakthrough analyzer. After that, again, we compare with the DVS vacuum system, and the data are very consistent. Again, means the high accuracy of the breakthrough instrument. After that, we do the consumption of CO2 and water. And the relative humidity, we select is 30% and 60% here. And from the figure here, you find that CO2 breaks through very fast at the beginning, and the retention of the water is long time. So that means this material have higher affinity towards water than CO2. And from the capacity calculated here, you can easily find that compared with the CO2 capacity under dry condition, becomes negligible. So here is the comparison of the capacity. So these results tell us, well, under dry condition, 39 zeolites is very good for CO2 absorption. But with the presence of water, all the CO2 is replaced by water. And well, if I'm the customer, I will not use this type of material for CO2 capture. And after that, we do the regeneration for the materials. For example, here we increase the temperature from ambient to 200 degrees C. And here are the disruption profile for water and CO2. And for this figure, actually, you can have several informations. For example, if you integrate the area here, you can get the disruption amount of the specific gases. For example, the water or CO2, and you can compare with the absorption capacity, and you will have an idea if it is reversible or not. And from the temperature, the molecules dissolved here, it can also tell you that there will be different sites existed in the material for gas absorption. For example, CO2 dissolved very fast at low temperature here. That means very easily to be regenerated. But for water, you can find that the disruption covers almost the whole heating process. And you can find different peaks appears here. So that means in this type of material, there are different sites with different strength for water absorption. Okay, so after that, we do the cyclic test for this material. They repeat the test, and you can find that all the test here, it is very reversible. So this can tell you during either heating or exposing to water, this type of material is very stable. Okay, so next application is about the DAC, direct air capture. And this one, very simple. People only want to capture the CO2 from the atmosphere. And the condition of the CO2 is 400 ppm. And for water, it's just the ambient condition. So first, again, we use the DVS system, the gravimetric method, to measure the isotherms, and we find that for under the dry condition, the CO2 uptake, it is satisfactory. But with the presence of water, you can find almost all the CO2 again is replaced by water. And in this figure, I can also show the blank of the CO2 here. So this is the blank of the system. And if you compare with this and with the curve here, you will find it is very small that volume. And here is the comparison of the CO2 uptake under the dry condition and the wet condition. And very similar results. So here comes the summary of the CO2 capture. For zeolites, it is very good for CO2 capture under the dry condition, and it is very stable, exposing to water or under heating. But with the presence of water, the CO2 capacity nearly fully lost. Okay, so the next case study is about the toluene water absorption on 39 zeolites. So first, again, we also do the dry suction of toluene at 25 degrees C, and we do the cyclic test. The concentration of toluene we select is 800 something ppm. And here we also show the black data here. Again, it's very small that volume. And if you have a look at the cyclic test here, the data are very consistent. That means the absorption process is reversible. And for the absorption of the toluene capacity, It is quite stable among the 3 cycles. After that, we do the generation, and you can find that we do the generation at 300 degrees C. And, well, I should say all the absorbed toluene are dissolved during this process. And next, we also do the toluene absorption under the wet conditions. And this one, we combine the toluene and the 30% of RH in this condition. And the temperature is 25 degrees C. And from this data, you can also find that there is a roll-up area here, and that is the replacement of the toluene by the water. And if you look at the capacity here, it is quite different, much smaller than the absorption capacity under the dry condition. So after that, we also do the regeneration. And here you can also find that the desorption nature for toluene and water, it is also different. It is quite similar with CO2, I should say. The toluene dissolved at a low temperature, but for water, it continuously releasing, and with different temperature it released. That means different absorption sites. Okay, so here comes to the summary of the toluene absorption on the zeolite. So I should say it is quite similar with the CO2 absorption. Under the dry condition, you can get a very satisfactory absorption capacity between 1.95 to 1.98 millimole per gram. But with the presence of water, the toluene capacity reduces. So again, this reflects the hydrophilic nature of the zeolite setting X. Okay, so that is the end of my presentation. And at the end, I would like to introduce our full lab solution. So we have the carbon capture package in our company. If you would like to equip yourself with the cutting edge laboratory solutions, or provide the researchers of the lab, if you want to complete the lab setup, we can provide you the tools or knowledge or support. And we also have the package of the carbon capture, like with different levels of equipment. And if you are interested in this package, feel free to contact us. And we're also offering some contract testing, like if you are interested in the gas measurement or sample characterization, like the isotherms or bristle curves, feel free to contact us. Thank you very much.
Thank you, Lisa, for that very insightful presentation. We now have some time for questions. We can take a look at what our audience has asked. Please allow me just a few seconds to browse what has already been asked. Don't hesitate to post your questions in the chat under the send question to staff. That will arrive to us, and we will be able to take that question live or answer it directly in the chat. Okay, so just looking at the couple of questions that have already been trickled in here. The question is, how can you pack the column in uniform way each time?
This is a very good question. Well, I should say it really depends. If your material it is very uniform shape, I think it is very simple to do this, and you can mark the length of the bed and the amount of your sample you put inside. But if it is the shape of the material is not regular, or if it is not like the powder, something, the mixture of powder or the pellets, I should say it is very hard to uniform the column. Yeah.
Okay, so you very much have to consider the morphology.
Yeah, exactly. And I should say, depending on what are your interest, if you are interested only about the capacity, I should say how you're packing the materials. It will not affect that much of the capacity itself. But if you want to do some analysis for the kinetics or something, do some modeling, it will affect.
I see. follow-up to that question is, are there any sample configurations that are offered with the system, different column sizes or anything like that?
Well, we have the columns with different sizes. As I mentioned, we have small columns with the internal diameters of 2, 3, 4 millimeters. We also have the 10 millimeter internal diameter column. That's it. And to fix the samples in the column, you can use the cut spool. We will provide that.
Got it.
Yeah.
Okay. Just looking here, next question from the audience. What is the average amount needed for breakthrough analysis for CO2 absorption?
Average amount means the sample amount?
I believe so.
Yeah.
I guess either the mass or the volume which is available.
Well, I should say it really depends on the materials, depends on the capacity, right, or the density of your materials. And typically, I will recommend in the column, you need to pack around at least 3 to 4 centimeter length of the bed. That is my recommendation.
I see. Okay. Of course, it very much depends on the uptake capacity of the sample, like you just said. So yeah, just looking. Next question would be, what in your experience is an appropriate particle size or mesh size for the particles to avoid any pressure changes or pressure differences between the inlet and the outlet for the column?
Well, this is a good question. So typically, I only use the pellets for the measurement, and I should say it's if there is microns, several hundreds, that is okay. But if it is go further, you need to verify by yourself. Like we have the pressure indicators in the system, and you can find if the pressure is too high or not. If it is high, it's not recommended. And if the difference of the pressure indicator beyond to 20 torr, I will not recommend for further test.
That makes sense. Maybe I can add something from my experience is that you are able to pelletize the very fine powders by using something like an FTIR sample press. And after pelletization, those pellets can be ground up a little bit and used as they are. That will compact the powders together without usually leading into a loss of capacity, without also using a binder.
Yeah.
Okay. Next question. Based off of what you've shown in the section around Zeolite 13X, can it be modified to be a better adsorbent for carbon capture? How would you go about doing that?
Well, I should say if you use 13X itself as the solvent, I will recommend you use 2 columns, separate column. First is the water filter, capture water inside, and another column you can capture CO2. It works. And on the other hand, you can do some modification for the material. For example, you can do some like functional groups, like amine functional groups. I think it may help to my experience, but I didn't try because currently in 13X, the extra thermal cation is the sodium type, and I do not think that is good for the CO2 capture directly because as the data I show you, it is very hydrophilic. So if you can modify like the amine functional groups, that can enhance the CO2 suction with the presence of water. So that is my recommendation. Thank you.
That makes sense. Around the presence of water, a follow-up question on the experimental side from the audience is, do you have to pre-humidify the sample in order to run experiments in wet conditions? Is that how the experiments are run?
Well, This one depends on your interest, I should say. You can either use the dry samples or the pre-humidified. So if you want to evaluate, like, for example, the direct air capture, you may want to do the pre-humidified because that represents the nature of the samples you put in the ambient atmosphere, right? For example, you put the zeolite or something in the room temperature in the ambient condition. Sometimes it will absorb a lot of water. And if you want to further investigate on the top of this, is there CO2 can be further absorbed in our material? I will recommend you do the precondition. But if you want to only run the assumption in the for the dry samples, for example, during the cyclic test, every time it is under heating, and after that, all the water is removed. And if you want to evaluate the efficiency just after that, you do not need to pre-humidify your sample. You just put the wet gases into the system and start the experiment.
Okay, thank you for the comprehensive answer. Follow-up question, no, it's a standalone question. With the two-column configuration, can you do two experiments at the same time? And what are the conditions for those experiments?
Unfortunately, no. We can only run one column at one time. Yeah.
I see. There is an advantage on the two-column configuration, right?
Yeah. So we can say it is high throughput. You can, to save time, you can put the two columns inside to do the activation, or to save time, you do not need to come to swap the columns like during the weekends or something, but you can only run the sample one column one time.
I see. So it's setting up comprehensive experiments using one column at a time and activation, which is simultaneous. That makes sense.
Yes.
Okay. Would the device be able to run flue gas compositions?
Yes. The data I show you, it is the post-combustion. That is for the flue gas composition. Yeah, with the percent level CO2 and water inside, you can run the gas composition.
Okay. Are there any limitations to the concentrations that can be achieved and the contaminants that can be introduced at the moment?
Well, if you want to also study like the SOx or NOx, I will say you need further analyzers like the mass spectrometer. And if the CO2 concentration is beyond like 30% level, you may also need to use the mass spec or the TCD for the measurement. Yeah.
Thank you, Lisa. All right, we might have reached the end of the questions here. If anybody still has questions, please do not hesitate to post them in the chat. Maybe one question from my side here. In terms of the sensors that you've highlighted with the instrument in one of your slides, which one of those do come with the system by default?
Let me show you. For the sensors, you can still see my screen, right? Can you?
No, I believe we've moved to the holding slides. Now it should be possible. Yeah, we can see it.
Yeah. Okay. So the sensor here, for the CO2 one, by default, we only provide one, either the ppm level or percent level. And for the relative humidity, we will provide both for inline and outline. And for the PIDs, all the ranges we provide by default. For TCD, it's also by default.
I see. So the sensors that come with the device are a subset of those that were highlighted there. Okay. Okay, so it seems that we've missed the second part of a question here, a previous question. Can you have the different conditions in the first column to the second column?
Yeah, well, as I mentioned, it is a separate experiment, and you need to run the test individually. So you can do whatever you like on the first one and change another condition on column 2.
Okay, yeah. All right. So I believe this finalizes the questions from the audience. So thank you again, Lisa, and thank you to everybody who joined us today. We hope you found this webinar on breakthrough analysis valuable. If you have any other questions, would like more information, please feel free to reach out to us at info@surfacemeasurementsystems.com or on our website, www.surfacemeasurementsystems.com. A reminder that a recording of this webinar will be available soon on our SMS Sorption Academy online portal. Please make sure you're registered to have access to this and to other informative webinars, application notes, training materials, etc. That said, wishing everybody a great end of the day or start of the day, depending on where you are in the world. And of course, all the warmest wishes for the upcoming holiday season. All the best.
Thank you. Thank you very much.
Thank you again, Lisa.